Welcome to our session on quantum many-body spin Hamiltonians. Today, we are going to focus on how we can understand quantum many-body systems, and in particular, the case of quantum many-body spin models. We are going to understand what is the difference between classical and quantum magnets, and how can we see transitions between classical and quantum magnets directly from a quantum many-body Hamiltonian. We will see how we can understand different types of expectation values from the ground state and excited states of the many-body wave function of a quantum magnet. We will see how we can associate those different expectation values to phase transitions between different types of quantum magnets or between classical and quantum magnets. So let us start with understanding how can we go from classical magnetism to quantum magnetism, and what is the difference between the two of them. When we have a classical magnet, we many times can describe it with something called an Ising model. This is a model where the Hamiltonian is just a product between two spin operators. This is SC in the first side and SC in the second side. So there are no Sx nor Sy terms. You can think that these operators here are just operators in one of the spin directions of a quantum spin, or you can even think that they are just Ising spins, meaning variables that can take values +1 or -1. So from that point of view, this is a classical statistical model. If you now start asking yourself, how can I minimize the energy of the Hamiltonian, then you can very easily see that the ground state that minimizes the energy is actually not unique, and that there are two ground states. And in particular, there's one ground state where this first spin points up and the second one points down, and then there's another ground state that it's the exact opposite. Each one of these ground states breaks time reversal symmetry, meaning that if you apply time reversal to this object, you don't get the same object, but you get the opposite one. But of course, the set of ground states does not break time reversal symmetry. A classical magnet is essentially a macroscopic version of this. It's a state that essentially has spins pointing in very specific directions in each different site, and the ground state breaks time reversal symmetry, and we have a finite magnetization in each site. A quantum antiferromagnet is completely different. So a quantum antiferromagnet is actually described when you replace the S set operators by all the Sx and Y and S set operators at the same time. And this gives rise to what is called the Heisenberg model. Now, we need to understand that these S0 and S1 are actually quantum mechanical operators. So these are the operators of the angular momenta that have the typical commutation relations. And if you now ask yourself, what is the many-body wave function that minimizes this Hamiltonian, what you actually easily see is that the many-body wave function that minimizes the Hamiltonian is actually what it's called the singlet state. So it's a state that it's a linear combination between up-down and down-up, that it's antisymmetric, and what is most important, it is unique. There's only one ground state that minimizes the energy of this Hamiltonian, hence the name singlet. Something that is very important about this singlet state is that the magnetization on each side is 0 from the point of view of the expectation value. And this can be very easily understood by realizing that in this many-body wave function, there's the same probability of the first spin to be pointing up, then pointing down, and the same for the second spin. You can think that this Hamiltonian is the simplest example of a quantum magnet. And from now on, quantum magnets are going to be, for us, just generalizations of this type of ground state. They are going to be essentially a macroscopic version of this many-body wave function, of course, much more complicated, of course, featuring singlets between many different sites, but in practice, a generalization of it. So if we now start asking ourselves, well, what happens if we go to bigger systems? What happens if we have L sites instead of just 2 sites? So in that case, we will, of course, have more than one exchange coupling. We are going to, in general, have a set of exchange coupling between sites I and J. And let's say for the sake of concreteness, we can think that these Ji and J are essentially the exchange couplings that we would have in a system that it's form as a chain. So there's only first neighbor exchange coupling. From the point of view of solving the Hamiltonian, regardless of what is the choice that we make for these JIJs, what we actually have to do is we need to take a basis of the many-body Hilbert space. We need to write the Hamiltonian in that basis, and we need to diagonalize the Hamiltonian in that basis. So in the case of just two sides, the elements of the basis are just all the possible combinations of up and down for the two sides. So we have up, 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 down, down, up, and down, down. We have three sides. The elements of the basis are going to be all the possible combinations of up and down, and in particular 8 combinations. So this is effectively just 2 to the 3. And if you keep making the system bigger and bigger and bigger, and for example, you go to 4 sides, then instead of having 8 elements in the basis, you have 16 elements in the basis, effectively 2 to the 4th power. And of course, as you make the system bigger, then the elements of the basis, the number of elements of the basis keeps increasing, and in particular, it increases exponentially with the system size. And this exponential growth of the elements of the basis for this quantum many-body Hamiltonian is what makes quantum many-body physics and quantum magnetism so challenging, especially when you go to systems that are made of many, many sides. For our purpose in this lecture, we are going to deal with systems where we can actually write the exact Hamiltonian in the full many-body Hilbert space. So in practice, we are going to deal with systems with up to 20 spins. So L is going to be 20 at most for us. In the next lectures, we will see how we can actually go to much bigger systems using tensor networks to help us to parameterize this exponentially large Hilbert space. But for this lecture, let us focus on the small systems. Okay, so for us, the objective is simply to take this Hamiltonian, write the Hamiltonian in the many-body basis that has 2 to the L elements. And once we have the Hamiltonian in this many-body basis, we try to find the ground state and perhaps some excited states. And the way the ground state or excited state is written is just as a linear combination of the different elements of the basis. So from a computational point of view, we just have to determine all these coefficients. And this is something that we will do just with exact diagonalization for the small system that we are going to consider. So our wave functions are going to have 2 to the L coefficients, and our Hamiltonians are going to be effectively 2 to the L times 2 to the L matrices. Okay, so let us now look at some very specific quantum many-body spin Hamiltonians to understand what information we can get from the Hamiltonian, which information we can get from the ground state. And let us start with a minimal quantum magnet. So we are going to take a Heisenberg model. So we have products between spin operators in site n and spin operators in site n plus 1, and all the exchange couplings are 1 for nearest neighbors. So site 1 is coupled to site 2 to site 3, 3 to 4, and so forth. So the first thing that we can do is look at the energy spectra of the Hamiltonian as a function of the system size. So for this, we take this Hamiltonian, we write it in the many-body basis, and we diagonalize it. And what we are plotting here are just the eigenenergies of the Hamiltonian once we have diagonalized the Hamiltonian. So you see that for a system size with 2 sides, you have, let's say, a couple sets of eigenvalues. For 4 sides, you have more. For 6 sides, you have more. For 8 sides, you have more. And actually, the number of eigenenergies that you get here grows exponentially with the system size. It is exactly the same growth as the dimension of the matrix. In principle, when we are interested in quantum many-body systems, we want to focus on the lowest energy eigenstate. So in this state over here, in this state over there, and this state over there. And if we look at excitations, we want to focus on the excited states that are closest to the ground state. So this one over here, this one over there, and this one over there. Usually states that are very high in energy are not, let's say, relevant for experiments, because our many-body system is going to be in a combination of these 2 states, and if we are at ultra-low temperatures, only on this state. So from now on, let us focus on observables related with low energy states. And if you look at this many-body spectra, you can already identify something that it's called the many-body gap. So this is effectively the difference between the lowest energy state, that is our ground state, and the first excited state. And in particular for this Hamiltonian, you see that this gap actually decreases as you make the system bigger and bigger and bigger. And as we will see later, this actually decreases as a power law because the system is gapless in the thermodynamic limit. Okay, so to start with, let us think about a slightly generalized Heisenberg model. So we are going to take a Heisenberg model where the couplings between the x and y directions are different from the couplings in the z direction. And the interesting point about this Hamiltonian is that you can think that this Hamiltonian describes a family of Hamiltonians that in one limit is a purely classical model, namely the Ising model that we discussed before, and in another limit, this corresponds to the purely quantum Heisenberg model. So this Hamiltonian effectively allows us to interpolate between a classical limit and a purely quantum limit. And we can actually see this transition from classical physics to quantum physics just by looking at the interpolation of this Hamiltonian. This is a very important Hamiltonian that is known as the XXC Hamiltonian. Okay, so the important thing for us is that this Hamiltonian effectively has, let's say, two different regimes. It can have the classical regime, which is the regime where Jxy is 0, so we only have coupling in the z direction. In this case, we recover the Ising model. And it has the quantum regime, so the regime where Jxy is equal to 1, and we recover the purely Heisenberg model. The important point is that in the thermodynamic limit, when we are in the Ising model, our system is doubly degenerate, meaning that it has two ground states, the up-down and down-up. This is just a macroscopic generalization of the Ising dimer that we discussed before. And when we have Jxy equal to 1, then we are in the Heisenberg limit, and in that case, our ground state is unique, and it doesn't break transversal symmetry, and it represents effectively a linear combination of different singlets in the system. So it's a purely quantum magnet. And this transition between the symmetry broken state and the Heisenberg limit actually happens at Jxy in the thermodynamic limit. We're not going to be at the thermodynamic limit, but we will see how we can already see signatures of this in finite size systems. Okay, so this is the let's say energy spectra as a function of Jxy. So in this limit, over here, you are in the Ising limit. In this point over here, you are in the Heisenberg limit. So if you follow the evolution of the eigenenergies, you actually see that in the Ising limit, your ground state is doubly degenerate, right? So there's this eigenvalue over here that goes to 0, and then there's, of course, the ground state. So in the Ising limit, we have a doubly degeneracy. And of course, this keeps happening when you go to the thermodynamic limit. If you now go to the Heisenberg limit, what you actually see is that one of the eigenstates gets a finite energy, and you end up only with a single ground state. And this kind of departure happens, let's say, somewhere around 0.3 for a system with size 10. If you go to a slightly bigger system, you see very similar phenomenology. What now actually happens is that this splitting of the originally two degenerate states happens a little bit later in Jxy because you made the system a bit bigger, and if you keep making the system bigger and bigger and bigger, you can actually see that in the thermodynamic limit, this splitting happens exactly at 0.5, which is where the phase transition is. So the spectra of a many-body Hamiltonian already allows you to see if there might be some phase transition between two completely different states. Okay, so now let us focus on the minimal case of a quantum magnet. So we are going to take a dimer that has coupling of the Heisenberg type, so S0, S1 with all the different spin components. A very simple way of understanding the spectra of this Hamiltonian is by thinking that you can actually define an effective angular momenta that is S0 plus S1. And when you define this effective angular momentum, you can see that you can rewrite this Hamiltonian as L square. And this L square has a set of eigenvalues that is L times L plus 1 plus some, let's say, offset of the energy. And in particular, this gives rise to different sets of eigenvalues, what we call the singlet, that is our, let's say, ground state, and what we call the triplet, that is the excited state, and in particular, a set of 3 excited states. The singlet corresponds to S equal to 0, or if you think in terms of this L equal to 0, whereas the triplet, namely the set of excited states, corresponds to L equal to 1. Okay, now let us see how we can actually see signatures of those states directly by looking at the spectra. So here, what I'm plotting is how the many-body spectra of the Heisenberg dimer changes as you add an external magnetic field, so a magnetic field that affects all the spins. Something important to note is that this Hamiltonian actually commutes with the total spin operator, and what this actually means is that the eigenstates of this Hamiltonian are the same as the eigenstates of this full Hamiltonian. So we are not creating any sort of mode mixing by adding a magnetic field, but we are just actually splitting the eigenvalues of the Hamiltonian. So at magnetic field equal to 0, what you actually see is that there's the ground state over here, and there's the set of 3 excited states over there. This is what we called before the singlet state. This is what we called before the triplet state. As you increase the magnetic field, you see that the triplet state now branches out. So the 3 states get a different energy. And the reason why they get a different energy is because they have a different value of the total spin in the z direction. The state that remains completely constant is a state that belongs to the triplet, but has a net 0 spin in the z direction because it's this linear combination. And this state that goes up in energy has a total spin up, up, so equal to 1. And the other one that goes down has a total spin equal to -1. And therefore, thanks to this, let's say, finite spin, you get a linear evolution of the energy as a function of the magnetic field. This is actually much more clear if you start computing expectation values of your many-body states. And in particular, expectation values are an incredibly helpful tool to actually understand how your many-body states are. And this is essentially what we are going to use from now on. So if you look at the expectation value of the set component of the spin, so the sum over all the sides, and in particular 2 in this case, what you actually see is that the state that goes up has a total spin equal to 1, the state that goes down has a total spin equal to -1, and the singlet state has 0, and the other state from the triplet also has a set equal to 0. So here you can very easily see that the evolution of these states corresponds effectively to what you were expecting from these many-body wave functions. Okay, so now this expectation values of the spin operator allows us to understand more complicated many-body spectra. So in particular, we can take, again, our Heisenberg model and go to slightly bigger systems. So we can take both 6 sides and 10 sides. And if we go to these bigger systems, you actually see that you start having many, many different states now. So here what we are plotting is no longer the energy, but actually the energy minus the ground state energy. And what you actually see is that if you are at magnetic field equal to 0, you have a ground state that is effectively your singlet. But then as you increase the magnetic field, one state that has a finite magnetization starts approaching the ground state, and eventually it becomes the new ground state. So in this region, your ground state actually has a finite magnetization. As you can see here, if you can keep increasing your magnetic field, then another excited state that has an even bigger magnetic moment becomes the ground state over here, and so forth. And if you go to an even bigger system, you see that these transitions between spin equal to 0, s equal to 1, s equal to 2, and s equal to 3, they happen even sooner in terms of the magnetic field. So what you observe here is that these expectation values allow you to see when there's a change of your ground state. Your Hamiltonian commutes with a total spin operator, and therefore you are not changing the eigenstates of the Hamiltonian when you add a magnetic field, but what you are changing is actually the order in energies. So when you are at 0 magnetic field, your ground state has no magnetization whatsoever, But when you add a magnetic field, you may actually end up with a ground state that has a finite magnetization. This can be 0, 1, 2, 3, and so forth. This is actually something that you can also see by directly looking at the ground state and excited states in the presence of a small magnetic field. So what we are taking now is, again, our Heisenberg model and a very small magnetic field. This is not large enough to create a phase transition, so to create a switching between who is the ground state, but it is large enough just to create a small splitting. So with this small magnetic field, what you get is that your ground state has zero magnetization everywhere. So it's a singlet state or a, let's say, complex combination of singlets. Then your first excited state is a state that has in total a set equal to 1. But actually, if you look at the magnetization per site, the magnetization lives everywhere. So it's a total, it's a set that it's non-zero, but it's distributed in the whole spin chain. And then the next excited state is a state that has S set equal to 0 everywhere. So in a way, it's like the state that had S set equal to 0 in the triplet. And then you have another excited state that also has finite magnetization, but that is distributed everywhere. And that, interestingly enough, it has the exact opposite profile as this one. And this, of course, is expected as this state is effectively a time reversal of this other state. And if you keep going to higher and higher excited states, you actually see that your magnetization, again, is distributed in the whole system. You can get excited states with magnetization everywhere, with no magnetization, with the opposite magnetization, no magnetization, and so forth. So what this actually tells you is that when you look at excited state, there's a whole family of states that have spin excitations in different parts distributed in the system. This is something that we will also address later on. Okay, so you can actually see this transition between ground states very systematically if you plot what is the expectation value of the magnetization on each side as a function of the magnetic field. So you take the ground state and you compute the ground state for every single magnetic field. And with this ground state for every single magnetic field, you compute the magnetization on every single side. So at B set equal to 0, you are essentially in the case where no magnetic field exists, and your ground state is a singlet that has 0 magnetization everywhere. Now you start increasing a little bit of the external magnetic field, and at a certain point you create a phase transition. So you switch who is the ground state, and then a state that has some finite magnetization becomes the ground state. You keep increasing the magnetic field, and another switching happens, and you get another state that has a different distribution of the magnetization, and so forth. And eventually, when your magnetic field is very large, and in particular is larger than the exchange coupling of your Hamiltonian, then you get a saturated magnetization everywhere. And if you now go to the opposite magnetic field, you get exactly the opposite picture. So the switchings happen exactly at the same values, but now the magnetizations of your ground states are the exact opposite. A very useful way of looking at excitations in quantum magnets is by looking at something called a dynamical spin correlator. So the dynamical spin correlator is also one type of expectation value, but it's a slightly sophisticated expectation value. So you take your ground state, you apply a spin operator. Now you put a delta function of the frequency minus the Hamiltonian, and again the spin operator, and then the ground state. It is much easier to understand what this actually means if you just represent the delta function in the basis of eigenstates of the Hamiltonian. So if you now take your Hamiltonian and you think how this object looks like in the diagonal basis, what you actually observe is that in the diagonal basis, you effectively have just eigenstate of many-body Hamiltonian, eigenstate of the many-body Hamiltonian, and then a delta function of the frequency minus the energy difference between the excited state and the ground state. So what this object tells you is what is the probability or what is the overlap of creating a spin excitation in site n and at frequency omega. What this actually means is that if you have an excited state at energy omega that it's related to the ground state by spin excitation, then you get a non-zero value of this. And if you don't have any excited state that fulfills that condition, then you don't. Okay, let us look at how this looks like for the spin models. So let's take, for example, a spin 1/2 Heisenberg models, or the same spin chain as we used before. So if you take, for example, a system with L equal to 6, what you actually observe is that this dynamical correlator is, let's say, 0 up to a certain energy. At a certain energy, you get a profile that lives in the whole chain. Then you have a gap, then you have a different profile, then another gap, then a different profile, and so forth. What this actually tells you is that if you insert in this system an energy omega that is exactly this one, then you can create this spin excitation. If you inject an energy omega that is exactly this one, you can create this spin excitation, and so forth. So these profiles that you see here are very much related to the profiles of the magnetizations that you observed before. And in the case of spin 1/2, if you keep making the system bigger, so if you go to a system that has 10 sides instead of 6, what you actually observe is that your excitation goes slightly down in energy, so it gets closer to the ground state. And of course, the bigger the system, the more excitations you have. So in a way, these kinds of dynamical correlators that you see here reflect similar physics as when you have a particle in a box. So you can think that these profiles over here are the particle in a box excitations of a quantum magnet. Something interesting of these dynamical correlators is that they allow you to see relatively non-trivial behavior. So if you look now at a spin 1 instead of a spin 1/2, what you actually see is that the profiles are slightly different. And what is important to understand these profiles is that spin 1/2 Heisenberg models are gapless in the thermodynamic limit. So they are effectively a system where you have spin excitations with energies as small as you want, both in the edge and in the bulk. Spin 1, in contrast, is completely different. Spin 1 Heisenberg model is also a quantum magnet, but it's what it's called a topological quantum magnet. It's a quantum magnet that has a full gap on the bulk, even in the thermodynamic limit, and at the edges, it has gapless excitations, and most importantly, fractionalized excitations. This phenomena is very hard to see from small size systems, and we will need to go to much bigger systems, but actually one can already see some hints in this plot. So if you look at, for example, L equal to 10 to start with, what you actually observe is that there's a very strong excitation at very small energies at one edge and the other edge, and that excitation is weaker when you look at the bulk, and then the next excitation is at a relatively large energy. And if you compare L equal to 6 to L equal to 10, you can actually observe that while L equal to 6 also has this edge excitation, the energy of the edge excitation becomes smaller as you make your system bigger. And in particular, if you keep increasing the size of your system, what actually happens is that this spin excitation will live only at the edge, and it will have a 0 weight in the bulk when you go to the thermodynamic limit. And the next excitation in the bulk is going to be at a finite energy. But we are going to see this more clearly when we compute the very same system with many more sites using tensor networks. Okay, so let us go back to spin 1/2 Heisenberg models, which are the simplest types of Heisenberg models. What we are going to consider now is two different types of Heisenberg models. So up to now, we've been thinking in terms of a system that has a uniform exchange coupling. So the exchange is exactly the same between every single pair of sites. And what we are going to consider now is also a system that has a dimerized coupling. So a coupling that it's first strong, then it's weak, then it's strong, then it's weak, and so forth. And these two models actually have relatively different physics. So the model with uniform exchange coupling in the thermodynamic limit is gapless, meaning that you have excited states with as small energies as you want, whereas the system that it's dimerized in the thermodynamic limit has a gap. And the way to understand that it has a gap is by thinking what would happen if this red coupling was much bigger than this green coupling. Then in that case, you would have effectively one singlet formed by these two sides, another singlet formed by these two sides, another singlet, and so forth. And those singlets would be weakly coupled via this coupling. So you would have effectively a gap that is almost your singlet triplet gap. What's interesting about this model is that this value of the dimerization delta effectively allows us to control what is the gap of this quantum spin model. So these two models are both quantum magnets. They both have a ground state that is singly degenerate, but one of them is gapless and the other one is gapped, and the size of the gap can be controlled by delta. Okay, so this size of the gap is actually something that is very important when one looks at systems that are bigger and bigger and bigger. So for example, if you think about the dimerized model, you can take delta equal to 0 and go to the completely uniform limit. And if you go to that limit and you start computing what is the many-body gap, what you actually observe is that the many-body gap is, first at the beginning finite, of course, for two sides. So this is the singlet triplet gap. Then it becomes a smaller, then it becomes a smaller, and then it becomes a smaller, and so forth. And as you make the system bigger and bigger, it becomes every time smaller, but the way in which it decreases is actually fairly slow. And actually, it follows a power law behavior, so a 1 over L behavior. So around this system size, you are getting close to what you actually can compute with exact diagonalization in a classical computer. And you see that even in this limit, you cannot be convinced that the system is gapless. Whereas if you actually have a model that has a gap, this gap actually creates a new length scale. And this length scale is essentially telling you how big do you need to make your system in order to see that your gap has saturated to the value in the thermodynamic limit. So for example, if you take a finite delta and you start computing again what is the many-body gap, what you also observe is that your many-body gap becomes smaller as you make your system bigger and bigger, but roughly around 12 or 14, it has already saturated. And if you keep making your system even bigger, you will see that the gap, it remains constant at this value. The reason why this convergence is much faster is because if you have a gap, then the gap in a finite size system actually converges exponentially. And this is something that will be more clear when we compute much bigger systems using tensor networks. So now the question is, how can we see this from some sort of observable? How can we make some type of measurement that allows us to distinguish whether we have a system that is gapless or a system that is gapped? Because in the slide that I showed you before, we were actually comparing different system sizes, right? And if you have a single system size, we cannot be sure. So the way to do this is actually by looking at the response of the system. So the trick is relatively simple. So imagine that you take your uniform chain with your first neighbor exchange coupling, either dimerized or non-dimerized, and now you create a very localized magnetic field on one of the sides. You can think that you are effectively just putting an icing impurity in one of the sides of your chain. If you do this with the uniform chain, so with the chain that becomes gapless in the thermodynamic limit, what you actually observe is that after putting this local magnetic impurity, your system suddenly develops some magnetization. The magnetization, let's say, decays with distance. So as you go further and further away from your impurity, it becomes smaller and smaller, but it decays in a relatively slow way. And in particular, it decays following a power law behavior for a reason that is very similar to why we obtained power law in the previous slide. Whereas if you look at the dimerized chain, what you actually observe is that you also get a finite magnetization, but your magnetization decays much faster. And in particular, it decays following an exponential behavior. And the length scale that you get in this exponential is roughly the same length scale as the one that you would have in the gap before. So just by looking at the response of a system when we put a magnetic impurity, we can know if our system is gapless in the thermodynamic limit or if it has a gap. If the decay of the response is power law, then it's gapless. If the decay of the response is exponential, then we have a gap. This is something that can be systematically computed without the necessity of putting an external impurity. This is something that we can do by computing the so-called non-local static correlator. So what we actually do is we no longer compute the expectation value of one operator, but we compute the expectation value of two operators at the same time. So we compute expectation value of spin inside J and spin inside I. And formally speaking, we remove also this expectation value. Of course, in a quantum magnet, this is zero. So if you are dealing with quantum magnets, you can just focus on this term. Now, if you have a classical system or a product state, this expectation value is zero because, I mean, you can effectively factor out all these two terms and you get zero. If you have a quantum magnet, then this is not zero. And from the decay of this non-local correlator, you can see if you have a system that is gapless or a system that is gapped. If your system is gapless, then this non-local correlator is going to decay following a power law behavior. And if your system is gapped, then this non-local correlator is going to decrease following an exponential behavior. And actually, this non-local correlator is in a way mathematically equivalent to measuring the magnetization in one side when you put a perturbation on another side. This non-local correlator is effectively what you would get if you apply Kubo formula to the previous slide. Okay, so now we can look at this non-local correlator for our dimerized model, and we can take different types of dimerization. So we take dimerization equal to zero, we see that our non-local correlator, let's say, starts decreasing, and of course it goes to zero, but it goes following a power law behavior. If you put a little bit of dimerization, you see that it keeps decreasing, but now it decreases faster. And if you keep increasing the dimerization, then you see that for large dimerizations, your non-local correlator decreases even faster. So from the decay of this non-local correlator, you can actually infer what is the gap of your system, and in particular, the faster the decay, the bigger the gap of your system. Okay, so now let us look at quasi-particles in quantum magnets. And in particular, in this part of the lecture, we will see how we can link ideas from single particle physics to actually quantum magnets and to the emergent excitations of quantum magnets. So the basic idea is that we will try to get some sort of single particle description of a many-body quantum magnet. The ground state of this system is a purely many-body state, but there might be some single particle description for the excitations over this ground state. So we are going to assume that our Hamiltonian is a typical Heisenberg model and that our ground state is a quantum magnet, namely that has S equal to zero. And the idea here is to essentially make an algebraic replacement of these operators in the Hamiltonian and show that we can map this Hamiltonian to a single particle model. So the idea is relatively simple. So we are going to take the spin operators, this quantum mechanical spin operators, and replace them by auxiliary fermions, but something called Abrikosov fermions. So the idea here is that these new fermions are going to parameterize the same Hilbert space as the spins. These fermions, they are not electrons. They are fermions that have a specific constraint. And this constraint is that there has to be all the time a single fermion per site. Electrons can jump in and out of the sites, but these Abrikosov fermions or auxiliary fermions, they always have the constraint that there's a single fermion per site. And the reason why this constraint needs to be enforced is so that the dimensionality of the fermionic space is the same as the dimensionality of the spin space. So the spin space has a dimensionality of 2, you have up and down, but if you have spinful fermions, your dimensionality is 4. You have up, down, 2 fermions, no fermion. And this constraint over here essentially enforces that you retain the same dimensionality. So now the idea is that with this replacement, we can put it in the Heisenberg model and try to get some fermionic description of the Heisenberg model. So you replace each spin operator by 2 fermionic operators. So when you do this replacement, This effectively means that you have two fermionic operators over here and two fermionic operators over here, so four fermionic operators. Now, in these four fermionic operators, you use a mean field ansatz, so essentially replacing some of the two fermionic operators by their expectation value. And when you do that, you end up in a Hamiltonian that looks like this, where these Ki are effectively the mean field terms of your interacting fermionic Hamiltonian. So in practice, with this replacement, you can map a Heisenberg model to a fermionic model. What is important to note is that these parameters over here, they depend on the exchange couplings, and they need to be, of course, determined in a self-consistent way as they come from a mean field. But for our purpose, we can just think that there are, let's say, different potential types of, let's say, spin-on Hamiltonians, or different potential types of, let's say, dispersions for these spin-ons. So we can have gapless spin-ons. So we can think that there is a dispersion for the spin-ons, and our zero energy falls somewhere where we have a branch of spin-ons. And in this case, our system would be gapless. This is, for example, the case of the Heisenberg model that has a uniform exchange coupling. We could have gapped spin-ons. So we have a quantum magnet, but our lowest energy excitation actually requires some finite energy. This is the case, for example, of the dimerized Heisenberg model, where our dimerization effectively controls what is the gap of our spinons over here. And then, of course, we could have different types of dispersions for our spinons, and in particular, in two dimensions, we could have Dirac spinons. So in practice, you can actually think that the two Heisenberg spin-1/2 models that we consider can be also understood from their single particle spin-on Hamiltonian. So the uniform exchange coupling effectively gives rise to gapless spin-ons that have a Hamiltonian that is effectively a one-dimensional fermion in a chain, whereas the dimerized Heisenberg model gives rise to spin-ons with a gapped spectra, and this gapped spectra effectively stems from a dimerized tie binding model for the spin-ons.